Hi everyone. So in this video, we're going to talk about derivatives, and we are going to try to learn derivative from a visual perspective. And lot more time in our textbook or in our teachers, even in high school, was not having right tool to explain derivative because that era was different. There was not internet as good we have today. There was not a lot of visual channels available. Now YouTube has so much great content, right? So people can understand it in a better way. Everybody is connected. So now the knowledge transfer has been better. But I'm not saying it's our high school teachers' fault. They did what they could do in the limited resources. But somehow we lack to understand derivatives and calculus not in a right way, right? It is more formulatic and there's so much syntax and these kind of things. There's weird d by dx, there's integral sign, plus c, whatever. Like there are so much thing which we haven't understood. And I feel like in this digital world, we need to cover those things using the tools we have today. So we're going to understand derivative. This is a visual lesson. And then in this next video, we're going to learn the limits where the Leibniz, how the Leibniz did it, right? So I hope to see you in that one as well. So let's get started. So one example, if you have seen examples like the differentiation of x square is 2x, right? So what is this thing? What is even d by dx mean? Where this word d, for the first time when I saw this d by dx, like it was not part of a regular equation, right? I used to see equation like y is equal to mx plus c. Maybe there was sometimes square, cube, or logarithmic exponent. This made sense to me. But when I saw this d by d, what is this d over there doing, right? It's a weird way of writing differentiation. I generally prefer write fx and then put like a comma on the top of the hat. So that made me represent better, like that made me understand derivative better. But yeah, these terms were there and your book will be filled with these kind of thing. And so you don't have to worry about that. We're going to learn that as well. So let's get started again. And the example which I'm going to use it is there is a car which is moving quite fast. Initially, in 1 second it moves 1 meter. In 2 seconds it reaches 4 meter. In 3 seconds it reaches 9 meter. Basically, the distance is traveled by this car is kind of square of the time it is taking, right? So this is a weird car, just a hypothetical car which is traveling, and this is the like the example, right? So this looks like a function of distance and time, right? Wherein I'm inputting the time and I'm getting the distance, right? This is the function of that car. So we have also learned how we can represent function in coordinate plane. If you have seen that video, I think it's the sixth part of the sixth video of that series, right? That you can watch. So over there you can see how we can represent, and the way we do it is basically draw a coordinate plane where the y-axis will be distance and the x-axis will be the time, and these are the points which I mentioned you how car is traveling. There a time is taken over here and the distance I can see. So it looks like a square function, right? As I have already told you, take that the distance is square of the time. So the square function looks something like this. If you haven't seen it, this is like it, right? And our goal is to find the speed of this car, right? And we have learned the speed of the formula, like distance is equal to speed upon time, and then the speed comes like distance upon time, right? This is a general formula to find speed. And the speed, let's say a car travel 25 distance, this part over here, right? So what will be the speed over there? And the time it takes, it's like 5 seconds. In 5 seconds, it reaches 25. So I can easily calculate speed 25 meter per 25 divided by 5, it becomes 5 meter per second, right? And what does this means, right? What does this 5 meter per second means? It is an average speed, right? And when a car starts, like getting momentum or getting the acceleration, right? It doesn't start with a constant speed. It's probably start with a 0 and then it picks some speed or something like this, right? But the way we have found the speed, it's more like an average speed, right? So if I say that, like in a hypothetical scenario, car starts with 5 meter per second. In the 1 second time, it reaches 5 meters. Another second, it reaches 5 minutes. Another 5 meter. Another 5 meter, and it's constantly going. This is a hypothetical scenario. It's not true in the real world. And then if it is reaches 25 and we can count those time, it will become 5 and you can divide it and get 5 meters. So that's the average speed. And what we want to find is instantaneous speed at every microsecond. Like what was the speed of everything, right? Uh, so this instantaneous speed and derivatives are quite related. That we will see forward, like in 1 or 2 minutes. And if you see, it is not possible to start a car with 5 minutes. It always has to car. So what we can do is we can find uh, the speed at small portions, like maybe from 4 to 5 I can find speed. What was from 0 to 1 or 1 to 2, or maybe we can just take a big chunk from 1 to 2 or 2 to 4 or something, 4 to 6, something like this, right? We'll try to find the speed of these small time chunks, and that could represent the better answer for speed, right? And that we can start with basically. And yeah, coming to, before going to that, I wanted to add on that slope and speed are same in this example, right? If you remember, speed is basically a distance upon time, right? Which is basically the difference in vertical axis. If I have to see this line over here and there was 25 over here, right? If you see, if I have to find the speed, basically I'm dividing this part distance, this is 0 to 25 divided by 0 to 5, right? The difference in the vertical axis and difference in the horizontal axis, right? That I divide, and same way, if you remember finding the slope, slope is also same, right? Like rise over run, right? So rise is this part and the run over part. So in this case, slope and speed are the same thing, right? Finding slope and speed is the basically same thing. With this fraction is telling us speed and slope, right? And differentiation in the end, nothing is basically finding slopes at different like small time intervals, right? So that we can get the right picture of changing anything, right? So the car is changing, so we call it rate of change of distance with respect to time, right? How the distance is changing with respect to time, right? As I told you, right, how we gonna get better approximation or better result for the speed. So what we did, we tried to take this small time time unit, like time portion from 0 to 2, and I draw a rise line over here, and there is a, sorry, this rise line is basically from 0 to 4, and the run is 0.2, and then I draw a straight line, right? So I can find the slope of this straight line, right? This straight line, I can easily find the slope. We have learned in our previous video. The slope of this line would be rise over learn, that is basically 4 upon 2, the answer will be 2. So we can say that from 0 to 2, so you can see from the time from 0 to, the slope is constant 2, right? And that I have drawn. So in this graph, you can easily find at 1, okay, the slope was 2. At 0, the speed was 2 or slope was 2, right? And say where I can do for another time span between 4 to 6. And the rise over run over here, basically it is 16 minus, I think 4. This length will be 16 minus 4, right? Y2 minus Y1, we call it. That will be, I think, 16 minus 4, it will be 12. And then divided by 4 minus 2, that will become 2. So 12 divided by 2, it becomes 6. So we know that, okay, from time to interval 2 to 4, the distance was 6. And this is quite a good way to find. And note one thing is that we are finding the slope of this yellow line, not the orange line. The orange line is the goal to find. But if you see, they are very much close to each other. So this represent not the exact but approximate result of that thing, right? So finding the slope of this line actually is quite equivalent to the orange line. And there is very little. As you go far, the distance is going very little. But still, this is not accurate. You cannot start a car at two slope or something like this, right? The speed with 2 or something like this. Right? So what we're gonna do? We're gonna shrink this time. Now it was from 1 to 2, 2 to 4, and 4 to 6. We're gonna shrink it for 0 to 1, 1 to C, and then see that if our slopes are matching or not, right? Instead of finding the slope of orange line, if this yellow line coincide on top of each other, then that is more like accurate solution, right? That we're gonna see. So when we decrease this small time interval from 2 to, we go like the small, we call it x. Usually, what in the notation part, whenever we see this horizontal distance, we call it x, and this we call it y, right? So the difference, the time is represented by x over here, and this small difference is called like, what do we say, dx, right? The small difference between small time units, right? That we call dx, right? Small change, small time, right? 1.5 we are doing. And you can see in this example 1.5, this is quite overlapping. So this is more like an accurate solution you can get for slope and speed in this portion from 4 to 5. This is still, there is a gap little bit over here, right? But as soon we brought this difference dx, the difference in the time, as we go minute, instant, as we go more instant, very close to 0 or something, right? That time we will get better result. So for 1.5x it's more like this, and for 1 second dx, like the difference in the time, small portion of the time is 1, it more look like something like this. And you can see now the slope and the original curve for which we are trying to find speed and slope is quite overlapping. I cannot even see the orange line. So this is more accurate. As we go more smaller and smaller, there is less error, and we are actually finding slope of this tiny straight lines, right? It is not possible to find the slope of a curved line because there will be always a gap or something like that. But you tiny straight lines I can definitely find. So when the dx, the small time interval which we are trying to find, it's more looking like a proper line. Now for the difference, I think this is 0.1, I guess. And for that we have this line like this. And if you bring to 0.1, this line will probably look like a very straight line, right? And that will basically tell you the derivative of x square, derivative of x square to this thing. And it looks like a 2x. The equation of this line looks like a 2x. Right, and that is basically derivative, basically the rate of change of distance with respect to time. In the definition it is saying the rate of change of distance, like the way the distance is changing in this small time interval, we can find it like this, right? As the definition say, we did it, and this is the line. So for when the dx was 0.1 something like this, right, this line is like this, and this looks like a 2x line, right? If you have remembered from our function coordinate example how we can find the equation of this kind of line, and this is basically a function over here, and we can see the slope, right? We can find the slope for this point. As you can see, if I just pass 3, I'm getting 2, like it's twice the what is giving me, right? So the slope over here, if you find 6 divided by 3, then becomes 2x. And there is no intercept, it is as it is passing from 0. So we can tell it that this line represent basically the equation of this line will be 2x plus 0, right? No intercept. So the original function which we have x square, whose derivative, rate of change with respect to time is basically 2x. So this is the way we got that formula, right? And there is a different proof in the book which you find, which is the using limits and Leibniz. That is we're going to do probably in the next video, but this is to make you understand what the definition mean, how we can visualize the derivatives, right? So that is how we do it. Okay. Next I want to this part is kind of bonus part. If you don't even understand, that is completely okay. It's not much helpful, but it's just try to figure out how the notations are used, right? The d by dx, right? And probably the next video is the part where we will be going very deep into that and trying to come up with a rigorous proof about that. But still, just overview to get you introduction about that. So what do we see in our notebooks and everything is that this is a function fx, which is x square, and that is we called rate of change with respect to time, right? And we write it by d by dx of fx to x, and that becomes 2x, right? That we have seen in the previous part. And what this d by dx basically means, this is basically means this is the way we write, right? But somehow people like wrote like this, which makes sometimes confusing, like a mixed fraction kind of thing. But usually it's denominator upon numerator upon denominator, right? And what this dx part, dx, all we already know. This small times we call it dx, right? And if I have to elaborate it more, it will be probably like this. So just take a small number. Let's say I wanted to find derivative at 4, at this point 4. So I'll put x as a 4. So over here the x will be 4. And then if I have to find small distance, what I will multiply, delta is called the small part, right? X minus delta. So maybe it could be 0.1 or 0.2 something. So when I subtract x, let's say it was 4 over here, right? So this 4 minus this small delta point, right? 0, that becomes 4 minus 0.2 something, and that becomes 3.8 or something like this, right? So I'll do, and whatever the difference is, basically will tell me the small, what do you say? Small lines over here, like this. This is the 4 actually where I wanted to find the slope, and this is the another point, the small difference, so that I could get the dx. So this dx is basically this small tiny distance over here, right? And which we have written the form again using the same input as x. I'll find whatever the equivalent function output it will be. So if I put dx as 4, I'll probably get 16 over there, right? And if I put the difference, basically 3.8 or something, I'll get what I'll get 14.44, something like this. When you subtract this 16 minus 14 and then 4 minus 3, basically what these two numbers are doing is finding this tiny difference. The denominator is finding this tiny difference, and whatever the input we pass on to the x square function, that tiny distance over here, both tiny differences are small. And if I find slope over here, or in this example the speed is also same, speed and slope, because it is a very tiny difference, the slope will coincide on this curve, so there is not much error over there, and you can exactly get the slope at that point or speed at that point. And when you do that difference and when you solve it, you'll see that we get 7.8. if you solve this fraction, right, you'll get 7. So this d by dx is nothing. This part is telling the small tiny output. This dx is basically small tiny input which you pass to function, like small time interval gap, and then whatever the output you got, you like subtract it. D is for difference, small difference over there, and you divide it, you will get the slope over here, right, and the derivative at that point. So you get 7.8 because our difference was quite, it's not that small. I made it because just that guys can see that, but in real world or something, we have to go very close to 0.001 something like this, and we cannot go 0. If I go 0 over there, like 4 minus 4, it becomes 0. Then there is no solution for it. And whenever you find something like when there is no solution, then the limits and these all start coming into picture. And I don't want to distract you right now. Probably we'll do it in the second lesson of this part. But then the limits start into action, because then there will be no solution. Think about, like, if there was a 0 over there, right? And then becomes 4 minus 0, it becomes 0. 4 minus 4 becomes 0, and then dividing something by 0, there is no answer for it, right? Same we can try it for not only for 4. So this formula basically describes your derivative rate of change of distance at any point of the time, right? So not at the 4, you can apply it to some other value. Let's say we can do it for 3. Then 3 as well, I can just input those values. I can input that difference, small difference, 0.2. And when I solve it, basically dividing this small portion by this small portion, and I'll get 5.8. So these errors are, you can see it is reasonable because we have picked up this small value. But as soon as you go close to 0, you will see the exact solution 6, which is given by this formula, right? I hope that you have understood, if even 10% from this thing. That is the goal of this video, because in the next video we're gonna go all in and understand each and everything. I hope this video gives you a little perspective about how derivative works, what is rate of change means, right? In this example, speed and slope was the same thing, right? Probably you're gonna see more example. Why for x cube it was 2x x square, something like this, or maybe a logarithmic function. Maybe why sin x becomes cos x when we do derivative of this. And what is this even function? What is the problem with the notebooks is this, they just throw equation. We don't know where this equation comes from, what is actually doing, right? They'll give you, hey, this equation is sin x plus x square plus something, and solve the derivative order. Like if you see the NCERT books and everything, this is like that. And we don't know what the first place in this function is, right? In this case, we know this x square function is a function which denotes the distance and the time relation of a car, like how car is moving, right? And then we are trying to find the speed of things. So it makes sense what we are doing, right? There is a picture to there is a context behind every equation. And when you have context, you tend to understand things better, right? Because our brain works on stories, images and everything, right? So I hope you got good understanding of derivative, rate of change, slopes and all. so that we can build upon more things in the next video. And I hope you are subscribed for that. Leave me any comment or anything which you want to hear from me, or anything which you want to change or something like this, or any ideas you have. That will be really helpful for me. And I will suggest writing comments or something like this, because that helps me to boost this video, so that I could make more videos like this, right? So see you in the next one.
Who are you? My guy! I'm gonna become stronger than anyone around!